Okay, piecewise functions and making them continuous by thinking about limits. So if we look at this piecewise function, it's split into three sections. The section where x is less than 0, the section where x is between 0 and 2, and then the section where x is greater than 2. So if we think about the sections on a number line, we have our section where x is less than 0, so it's over here. And then we have our section where x is between 0 and 2, and this is how the function is defined on that section. So it's like right here. And then finally we have the section where x is greater than 2, and it's defined using that function. Okay, so we basically split the number line into three different sections. Now when we take the limit, a limit, it's just a matter of thinking about what section we're in. So for example, if I take a limit as x approaches 0 from the left-hand side of f of x. Okay, well think about what section I'm in. If I'm approaching 0 from the left, I'm approaching it like this, follow the red dot, right? So I'm approaching 0, I'm getting closer and closer to it from the left. Well, I'm in the blue then. That means I'm using this function. So what I'm going to do is I'm going to plug in 0 for x, so I get 2 times 0 minus 3a. Okay, so then it's equal to negative 3a. That's the limit as x approaches 0 from the left. What about the limit as x approaches 0 from the right? Okay, of f of x. Well, this time, again, going back to my number line, approach 0 from the right. I'm in this red section, so I'm going to use this function. This function. So I plug in 0 for x again. I get a times 0 squared plus 2b. So then our limit is just equal to 2b. Okay? So what does it mean for a function to be continuous? Well, what it means is that the left limit and the right limit are the same. They're equal to each other. So what we're going to do is we're going to set 2b equal to negative 3a. So we don't know what b and a are, but whatever a and b are, this is how they're related. 2b equals negative 3a. So since we don't have enough information yet, we should examine the other section, which would be the limit as x approaches 2. So let's look at the limit as x approaches 2 from the left and right. I'll do it down here. So we want to examine from the left and the right. If we approach 2 from the left, we're approaching 2 from the left, follow the red dot. We're in the red section, so we're going to plug in 2 to this function. So if we plug in 2, we're going to get 2 squared is 4. So we get 4a plus 2b. That's what our limit's equal to. And then 2 from the right, we're approaching 2 from the right. We're in the orange section, right? So that means we're going to use this function. So we plug in 2 for x, and we get 2 minus 4, which is negative 2. Okay? So now we have more information. We can hopefully use our information to solve for a and b. Because if this function is going to be continuous at x equals 2, then we need the left and the right limit to be equal to each other, which means that not only do we know 2b equals negative 3a from earlier, now we know that 4a plus 2b must equal negative 2. Okay, so this is like a system of equations, and there's obviously a couple different ways we can approach this. My first thought is we could solve for b here and then plug in and do a little substitution, right? Solving by substitution. So if we look at this piece of information, right, we know that b is equal, if we divide by 2 on both sides, divide by 2, we're going to get b is equal to negative 1.5a. So b equals negative 1.5a. And then what we can do is use that information here. So we now have that we have 4a. What's b equal to? B is equal to negative 1.5a. So we have 4a plus 2 times negative 1.5a. And that's going to still be equal to negative 2, right? We've just taken this b value here and replaced it with negative 1.5a, because that's what b is equal to. Okay, so we have 4a minus 3a equals negative 2. So let's finish this up. I'm going to move it over to a new screen. So just to recap, we had 2b equals 2b over 2 2b equals negative 3a. We divided by 2 on both sides to isolate b, and we found that b is equal to negative 1.5a, or negative 3 halves a. So we plugged that in for b in our other relationship. Let me see, we have 4a minus 3a, right? 2 times negative 1.5 is negative 3, equals negative 2. So a equals negative 2. All right, that's our first value that we know. Now, looking back, we know the relationship between a and b was that 2b equals negative 3a, so we should be able to solve for b. And we also know b equals negative 1.5a, right? So we can actually plug a back in here. So if we look over here, we have b equals negative 1.5, and what's a, right? A is negative 2, so we're just going to plug that right in right here, negative 2. So then b, it turns out, is 3. So if we go back to our piecewise function, to make this function continuous so there's no breaks in it, we need a to equal negative 2, and we need b to equal 3. So then we're going to rewrite this function with a and b plugged in. So looking at the function, we need 2x, and then negative 3 times negative 2 would be positive 6. So this is going to be 2x plus 6, right? This is going to be negative 2x squared plus 6, because again, b is 3, so we plug that in there. And then this is x minus 4. So with those a and b values, this graph is going to be connected. Very crucial that you go in that Desmos activity and mess with the sliders, make a negative 2, make b 3, and make sure you see that the graph is all connected, and then mess with them, make them not equal to negative 2 and 3, and see how that causes the function to break. These are the a and b values that will make this function always continuous. If you pick any other a and b, it's not going to be a continuous function always. There's going to be breaks in it.